Okay, so we are going to finish the course with the part dealing with finding weights for the delta in the case of ASEAN's basic ASEAN options. Okay, so let's share my screen. Okay, so let's come back to what I want to do. Here, I am in the situation where the payoff is given by a function of the Riemann integral of the trajectory of my risky asset. Okay, so it's what we call an ASEAN option, depending in some sense on the average, okay, of the whole trajectory of the risky asset. And we are here typically in the case where my option is path dependent, in the sense that in order to know my payoff, I need to know the whole trajectory. It's not sufficient, as in the previous case, to know the final value of the risky asset. And once again, what I want to be able to do is to write the delta or the gamma this way, okay? That is the expectation under an equivalent Martingale measure of the payoff multiplied by a random variable that I will call the weight, that will allow me to avoid finite difference scheme in order to compute the Greeks, okay? The beginning of the reasoning is exactly the same as the previous one. It tells you that the lemma 7 and the lemma 8 are the analogous of lemma 5 and 6 with exactly the same reasoning. That tell you that I have this kind of relation for any mapping F in such a way that the payoff is in L2, if and only if the relation is true for all mapping of class C infinity with compact support. Okay, so it means that I can suppose, if I want to prove this relation, I can restrict myself without loss of generality to F that is very regular, and here of class C infinity with compact support. And the argument is the same, okay? From the top to the bottom, it's because, okay, if I fulfill this, I fulfill this, so no problem. And to prove the converse, you are going to use approximations to approximate this F here, using mappings of class infinity with compact support, something that is okay because you have the density of this kind of mapping in L2. Okay, so it means that to prove what I want to prove with a weight that is independent of small f, I have only to prove the things, okay, for f of class C infinity with compact support. Second step, okay, second step. Once I know that I can restrict myself to things of class C infinity with compact support, okay, I know that the delta is the derivative with respect to the initial condition of the price function. That is given this way by this kind of payoff here. But if f is of class infinity with compact support, I have the regularity of what I have inside, in fact, here, and I can use once again Lebesgue derivation theorem. Okay, so for this one, if f is of class infinity with compact support, okay, I can internalize the derivation to obtain this. And now I can use, so this is using Lebesgue type theorem, and then using the chain rule, the classical chain rule, that is the derivation for compound function, I obtain the expectation of f prime, and I have the right to take f prime because it is regular, of the Riemann integral multiplied by the derivative of the Riemann integral. And once again, okay, so here I have to switch between the derivative and the Riemann integral. I have the right to do this, okay, here. And I obtain, using Lebesgue type theorem, multiply by the integral of the derivative of xu small x with respect to x. And I know by definition of the first variation process that here you have the first variation process. And the last point is because dxu x dx is by definition equal to yu of x. Okay, so I have this relation for the Greek, for the delta here, typically, in the case where my payoff is given by a function of the Riemann integral of the trajectory. And once again, okay, here I use Lebesgue type theorem to obtain this relation, and then I use the chain rule and the definition of the first variation process. So it means that to obtain the relation I want to have here, that is this relation with the weight, here, I can restrict myself now to the case where f is very regular according to these two lemmas. And I have this expression in the case where f is very regular. Okay, so I have this one that I can draw. Okay, and now let's prove the result in the case of the delta for basic Asian option. So this proposition is the same as proposition 9, but adapted to the case where, okay, the payoff is no more f of x capital T, but f of the Riemann integral. And I see that it will be possible to find weights of the form delta of W for a W that is in the domain of the square root integral, if and only if W fulfills this condition in terms of conditional expectation, a condition that is a little bit more complex than the one I have obtained for path independent option, but in fact the reasoning will be the same. Okay, so let's do the job here. So once again, I have an if and only if to prove, but as you will see, I will do the proof from the top to the bottom. And in order to do the converse, I will just take my reasoning at the end and to come back at the beginning. Okay, so let's do this one, okay? And the other side will be done exactly starting from the end and coming back to the beginning. Okay, so if I suppose that I have this, okay, I have my delta 0 of x that is equal to the expectation of f of the Riemann integral delta W. Okay, so what I can say is that from proposition 2, that is the chain rule for the derivative operator in the Malliavin sense, okay, plus proposition 6 that tell me that under good condition, the Riemann integral of a stochastic process, okay, whose values are in D, I can say that this one belongs to D. Okay, and so from the definition of delta, the square root integral, I can say that this is equal simply to the expectation of the integral between 0 and capital T, okay, of dt f integral between 0 and capital T xu of x du multiplied by wt dt. Here, it's simply the definition of delta and the fact that this random variable belongs to the domain of the derivative operator. Okay? What we are going to use now, it's the chain rule, the proposition 2. that tell me that, okay, to compute this one, I can use the chain rule. So let's use it. So it's f prime of the Riemann integral multiplied by dt of the Riemann integral wt dt. And now, using proposition 6, the proposition 6 tells me that I can switch between both the derivative operator in the Malliavin sense and the Riemann integral. So I have the integral between 0 and capital T of dt xu of x du. But I know that since x is the solution of the stochastic differential equation capital E, I have an expression for dt of xu, and that is the one I have proved here by proposition 8. I have what is dt of xu. I know what is dt of xu, okay? And I can write it now. And I can say where by proposition 8, okay, dt of xu of x is given by yu of x over yt of x sigma t xt of x indicator function t less than u. So I just have to plug this one inside this one, and I obtain what? I obtain that my delta 0 of x is equal to what? It is equal to, let's write it here, the expectation of this one, okay, that I can remove from the integral with respect to dt because it doesn't depend on the time t, okay? So let's write it first here. F prime integral between 0 and capital T xu of x dx, okay, multiply by this one. So I have an indicator function with u that is less than c, so it is the integral between, okay, so it is the integral between 0 and capital T, the integral between 0, so u is, so excuse me, so I have my dt xu du here, okay. So just have a look on the things. So let's write, so for a moment, so I have this, okay, integral between 0 and capital T, integral between 0 and capital T of this expression. So I can write if u is greater than t, I will write it this way. T and capital T, okay, yu of x sigma t xt of x over yt of x du wt dt. And this integral here, we copy the things here. So u here, okay, du. So here I first integrate with respect to u, and then integrate with respect to t. So I will change the order of integration. So it will be the integral between 0 and capital T, and I will first integrate with respect to t and then with respect to u. So integral of what I have y u x sigma t xt of x over yt x dt. Okay, but since I have changed the order of integration, okay, here it will be the integral between, excuse me, u is between small t and capital T, so t is in fact between 0 and u. Okay, and I have this quantity here that is independent of the time t, so I can remove it from the first integral to put it here. So it means that the expression I have here, this one, is exactly the one I have here. Okay, integral between 0 and capital T y u of x, integral between 0 and u of sigma t x t over yt, and I have just missed here the wt that I don't have copy here. So I will write it correctly here. So I can switch this one. I put the dt here, and I have wt that is present here. But from what I know from the previous lemma, from this one here, the lemma 8, I know that the delta has also this form here, in the case where f is of class C infinity with compact support. Okay, so from lemma 8, so the sketch of the proof, and if you have understood, is exactly the same as in the previous case. Huh? Lemma 8 tells me that the delta is also equal to f prime of the integral between 0 and capital T xu of x du multiplied by the integral between 0 and capital T, okay, of y t of x dt. So I have that this expression is equal to the first for all f of class C infinity with compact support. By definition of the conditional expectation, it means that the conditional expectation of the term in green here with respect to what I have inside here, given the integral between 0 and capital T of xu of x du, is equal to the conditional expectation of this term given this random variable. It's by definition of the conditional expectation that I obtain exactly the relation I am interested in here. Okay, so keep in mind that the reasoning I have done to do the proof of proposition 9 is exactly the same as in the proof of proposition 11 here is the same as in the proof of proposition 9. Okay, so I have done the proof and I have proved this part. If you want to prove the converse, okay, start from the end, because the equality between conditional expectation will give you what I have in yellow here, and you can come back to the beginning, okay, doing all the computation in the inverse order, okay? So you have a way here to characterize for W in the domain of delta, the fact that delta W is a weight to express the delta in my situation for my basic Asian option, okay? If and only if it fulfills this condition, okay? So I have this one, okay. So I have proved this result. A natural way is to say, okay, I have this result, that seems to be a theoretical result. Is it possible to find natural W in order to fulfill this condition? The answer is yes, and I propose to you here, okay, two natural candidates, and I will do the job for this one here. And for the other one, you will do it at home. To show that if you plug this one inside, it works with this equality. Okay, so suppose that you have Wt that is given by this one, y 2ytx square over sigma t xtx integral between 0 and capital T yu of x du. And we are going to plug inside here. And what we are going to prove is, in fact, that if I plug this W in this expression here, I will have the equality between this quantity and this one. And so I will have the equality between the conditional expectation. So if I compute the integral between 0 and capital T, yu x, integral between 0 and u, sigma t xt of x, wt over yt of x dt du, what I obtain in this situation. So I plug this one inside. So I will have simplification between the sigma. I will have the simplification between ytx square and the yt here. And so I obtain what? I obtain the integral between 0 and capital T, yu of x, integral between 0 and u of what? Of 2 ytx without the square, because I have a simplification between this one and the ytx here. Okay, so it is dt du and divided by the integral between 0 and capital T, the term that is here, yu of x du. Okay, so what is this quantity here? I see that here, so I integrate with respect to du here. So you have here a function of u that I will call g of u, okay? And here, what is this one? It's just the derivative of this one over 2. So this one is g prime of u over 2. So it means that I need to integrate with respect to u something that is of the form g prime u of the 2 over 2 multiplied by gu, but it's very easy to integrate this one because, okay, I have here a classical primitive that is the classical primitive of what? So I have this, so if it is, so it's not the good way to write, but I can write it this way, so, okay. So if I have j this way, okay, I have here g of u square that I have to take between 0 and capital T. So excuse me, so I have here g prime over 2. So it is, excuse me, so I have this one. Here, it's the derivative over 4 here that I have. Over 4, because when you compute the derivative of this one, you obtain 2 times this one, okay? And here you have 2 times divided by 4. So here, g prime g, so the primitive of g prime g is equal to g squared over 2, okay? So if I have this one, is it okay to have this g squared over 4 here, divided by the integral between 0 and capital T yu of x du. So the only thing I use here is the fact that u square prime is equal to 2 u prime u. Okay. So I have this one. So if I do this computation here, what I obtain this one between capital T and 0. So at 0, g of 0 is 0 from the form of this integral. It's the integral between 0 and 0. And at capital T, I obtain the integral between 0 and capital T of 2y t x dt square, okay, over 4, divided by the integral between 0 and capital T, y u of x du. So I have the simplification between the 4 and the 4 here. So the 4 here with the square simplify with this one. And I have the integral square divided by the integral here. And so I obtain the integral between 0 and capital T of yu of x du. So that is, if I take for w this weight, that is this one here, this one I have taken here. If I plug inside this expression, the value I obtain is none other than this one. Okay, so meaning that if I take this w here, it solves this equality, so I can take it to obtain a weight here. I can take delta of this w and I will obtain here exactly what I want. Okay, I will obtain exactly what I want. Okay, so I have this. So I have just so if I compute the derivative of this one here, just let me 1 second. I obtain 2 times this one. So here it's, excuse me, it's n over 2. Okay, that gives me exactly what I want here. Okay. Okay. So I have the 4 here. That is okay because I have an over 2 here. Okay. So I have proved that this candidate is a natural candidate to solve this equation. And so if I take the delta of W, it will allow me to have the expression for the weight in the case of the delta for the basic Asian option. Okay. So the last thing, so you have another candidate here. You can prove at home that it works, and it's easier to do than what I have done here. So to plug inside and to prove that it works, you have simplifications. It's very easy to prove here. Okay. And what we are going to do now in order to finish this session is just to see what happened for this weight and for the natural candidate I obtained for the weight in the case of the Black-Scholes model. Okay, so what I want to do now is to see what happened for this one in the Black-Scholes case. Okay. So for the Black-Scholes model, I remind you that yt of x is equal to xt of x over x, that sigma t xt of x is equal to sigma of xt of x, okay? And so if I replace what I have here by this here, the first natural candidate here is given by, so let's write it, 2 times xtx over x square divided by sigma xt of x. And if I want to express the y with the x, here I have the integral between 0 and capital T of xu of x du. And to obtain the y, okay, it's just divided by x here. Okay, and here it's sigma of x that I obtain this way. Okay, so I obtain simply this one here. Okay, so if I simplify a little, what I obtain by the 2 here, xt of x, because I have xt squared divided by xt. I have the sigma here, And I have the 1 over x squared multiplied by x. So I have 1 over x divided by the integral between 0 and capital T of xu of x du. I have this one here. Okay. So I have this expression of Wt in the case of the Black-Scholes model. If I want to obtain the weight, that is, my question now is to find delta of W. So what is delta of W? It is delta of this expression. So by the linearity, I can remove the constant. And I have to compute delta of the stochastic process xtx divided by the random variable integral between 0 and capital T xu of x du. So I have the delta of someone that is in the domain of the squared integral, okay, and divided by this random variable. If I come back to what I have done previously, and coming back to this expression here, I have the proposition 7 here that allow me to do the job. So if I use this proposition with u that is equal to x of small x, capital F that is equal to 1 over the integral between 0 and capital T xu of x dx, I can compute the delta I am interested in, that is delta of Fu using this expression. Okay, so let's come back to what I want. I obtain here using proposition 7 with u equal to x of small x here, and capital F is equal to 1 over the integral between 0 and capital T xu of x dx. I obtain for this one, so 2 over sigma x multiplied by what? So it is delta of x t of small x over the integral between 0 and capital T xu of x du minus the integral between 0 and capital T, okay, of, I can write it this way, xs of x ds of 1 over the integral between 0 and capital T xu of x du. And I do the integral with respect to s. So I repeat that I obtain this formula here. I obtain this formula using the proposition 7. You have 1 over delta of u, that is this one, minus the integral of the derivative of f multiplied by u. It's exactly what I have done in this slide here. So I will try to make this computation a little bit simpler here. So first of all, here I have something that is, this one inside here is progressively measurable. This one is progressively measurable, so the squared integral, okay, so it belongs to L2 prog. So this whole quantity here is none other than, the squared integral in this situation is none other than the Ito integral over this one. And it remains to compute this one here. It remains to compute this term. Okay? So we are going to compute this one to use the chain rule. So by proposition 6, this one is equal to the integral between 0 and capital T xs of x. So I use the chain rule to compute the derivative in the Malliavin sense of the inverse of the Riemann integral. Okay, that is what minus, because it's 1 over, so minus ds of the integral between 0 and capital T xu of x du divided by the square of what I have below. ds. Okay, but from the proposition, okay, so here it's not, it's the chain rule that I have here. Okay, so it's not the proposition 6 that I use here, but it's the proposition 2, the chain rule. Okay, that tell me how to compute the derivative of a function of this Riemann integral. And now from the proposition 6, I say that I can invert between the derivative and the Riemann integral here. So I have integral between 0 and capital T, xs of x, okay, with a minus. Okay, it's the blue part without this minus here, this one, minus the integral between 0 and capital T, xs of x, integral between 0 and capital X, ds of xu of x du over the integral between 0 and capital T xu of x du square ds. So it seems to be a little bit complicated, but you have here, okay, all the argument that you have to use in order to obtain this result. Okay, so maybe I will copy this slide and we are going to continue the computation in order to make it a little bit clearer. So I will erase the beginning, all these things here, and I obtain what? So for delta of W, I obtain what? So I have this very beginning here, 2 over sigma x, multiplied by this term that I can transform using an Ito and not a scored integral because the process inside here is in L2 prog. So I have integral between 0 and capital T of xt of x dbt over the integral between 0 and capital T of xu of x du minus, that is the minus that I have here, minus what? So minus minus, so I have a plus. Okay, I will write it this way, minus of this quantity, integral between 0 and capital T, xs of x, integral between 0 and capital T, ds of xu du over the integral between 0 and capital T, xu of x du square ds. I close the parenthesis and I close the bracket. And now I can erase all these things because it's exactly what I have reported here, the formula I have obtained. And now we are going to be interested in this quantity. So I have a double minus, so I will obtain a plus here. So what is delta of W? 2 over sigma x, the integral between 0 and capital T, xt of x dbt. The scored is the Ito in this case, integral between 0 and capital T, xu of x du, minus minus plus, integral between 0 and capital T of xs of x. And now I have ds of xu. But I know that ds of xu, okay, I will write it here, from the proposition 8, ds of xu of x is given by what? Is given by the integral of s less than u, y u x, sigma s xs of x over ys of x. So using this one here to compute this one, I obtain what? So I would write it this way. So the integral is an integral with respect to u. U is in fact greater than s. So I obtain the integral between s and capital T of what? So keep in mind that I am in the Black-Scholes model, so I have already done this computation here. In the Black-Scholes model, ds of xu of x, okay? I know in the Black-Scholes model that yu is equal to xu over x, okay? Ys is equal to xs over x, and here I have sigma xs, okay? So I obtain here indicator function of s less than u, okay? Sigma of xu of x, because I am in Black-Scholes. I keep in mind that I do this computation for Black-Scholes model. Okay. So I have this computation here. Okay, so let's replace this quantity in what I have obtained here. And I obtain the integral between s and t of what? Of sigma xu of x du. Okay, ds over the integral between 0 and capital T xu of x du. And once again here, what I obtain so this constant that can be put here, okay? And then I have, so I continue here the computation of this one here. So it is sigma, the integral between 0 and capital T. So I can also remove this one that is independent of the integration. Xs of x, integral between s and capital T, xu of x du, ds. Okay? And you have, once again, if you call this one g of s, you have here minus g prime of s, implying that this integral is equal to what? So to minus g squared of s over 2 that I have to take between capital T and 0. At capital T, this is equal to 0. And at the end, so my term in blue, this one here, so all this quantity is equal to sigma. So the integral between 0 and capital T of xu x du square over 2, it is the part coming from this one here, over the integral that is here, that is over the integral between 0 and capital T xu of x du. And of course, I have a simplification between this one and this one. So to summarize what I have obtained, at the end, okay, I can say that delta of W is equal to what? Is equal to 2 over sigma x, the integral between 0 and capital T, okay, of xs of x dbs over the integral between 0 and capital T xu of x du plus what? So I have plus sigma over 2, simply. So I have a real simplification this way. Okay. So my weight may be expressed this way. So the last remark that I want to do is a numerical remark that tell you that, okay, I know that the weight is given by this expression, and that, okay, in this case, I have my delta 0 of x that may be written as the expectation of f of the integral between 0 and capital T xu of x du, delta of w from the last proposition, okay, with delta of w that is given by this one. And the question is that, okay, I have a way here to compute delta using Monte Carlo methods, but the fact is, okay, how to generate independent realization of what I have inside here. So just to tell you that here, I have a Riemann integral. And in order to approximate it numerically, what I will do, I will approximate the Riemann integral by the related Riemann sum. So I can write it this way, T over N, the sum from K equal to 0 to capital N, okay, x k t over n x, okay, so I can do it this way, okay. I have n subdivision, so and the idea is just to approximate the integral. So you have the integral between 0 and capital T. You are going to consider a subdivision of step size, okay, capital T over n, okay, so we will have 2 capital T over n, and so on, okay. So you have this one, okay. So these Riemann integrals will be numerically approximated by this one, and so you will have just to generate the trajectory of the risky asset, okay, at these points, okay, something that you are able to do in the Black-Scholes model because you know exactly what is the distribution of the geometric Brownian motion, and the fact that in order to generate a discrete trajectory, you just have to generate, okay, in fact, a Gaussian vector that you are able to do according to what I have done in the introductive sessions, okay? And it just remains to have a look on this term because here you have Riemann integral and here you have an Ito one, okay? So I have this. So how to generate this numerically? But keep in mind, what is the stochastic differential equation fulfilled in the case of the Black-Scholes model by the risky assets? I have this. That is, okay, the Black-Scholes stochastic differential equation. Under the equivalent martingale measure. And I see that this term here appear here. So it means that we are going to be able to transform this Ito integral here using the x and a Riemann integral. So I can write this one in the following way. It will be x capital T of small x minus x over sigma minus r over sigma, the integral between 0 and capital T of x t of x dt. So in the case of the Black-Scholes, it's because I am in the Black-Scholes model, meaning that I have this stochastic differential equation. If I plug the thing here, I obtain this representation, and it means that I can approximate this quantity, once again, approximating this Riemann integral using this trick here. Okay, so this weight, and in fact, this random variable may be generated using a computer using the Riemann sum approximation of the Riemann integral for both the Riemann integral and this one that is in fact just a function of the Riemann integral, okay? So it means that you have just to generate discrete trajectory of the process in order to generate one random variable. If you do this several times independently, you will be able to use Monte Carlo methods in order to compute the delta in this situation. Okay? So it will close the course concerning the application of Malliavin calculus to Monte Carlo methods. And in the project I will propose to you, you will have some theoretical aspect to deal with, okay, in particular, some proof of the proposition that I don't have proof in this session. And you will have also for most of the project, okay, to compare for different type of contingent claim, and in particular for the weights I have obtained today, but the way they allow to improve the computation of Greeks. So for let's say path independent contingent claims, I have obtained some formula. For ASEAN type options, I have obtained some formula. And in most of the projects you will have, okay, we are going to focus on ASEAN option, and we are going to try to use the result I have obtained today in order to show how the Greeks are improved this way. Okay, so see you and bye-bye.